This is for Lab 7, the Earthquakes Lab, Earthquakes and Tsunamis. And this is for your activity that says Earthquake Machine. This is our Earthquake Machine. And I just want to clarify that this machine was not built for Geology 101. It was actually built for a structure class. So this gets into some pretty intense geophysics that obviously we're not going to cover. But I thought it would be cool to show sort of the principle of earthquakes along a subduction zone and how that happens, and what we have to fear from that, right? So how does an earthquake work exactly in a subduction zone? So we have this model earthquake table, and there are a couple components. If you don't fully understand this model, that's okay. Again, it's for an upper level course in geology, but I think that it really helps sort of drive the principles down. So you have a couple things here. You have bricks, which are going to represent the weight of an overriding plate or just any of the rocks, right? So these bricks represent the weight that is coming in contact with this subduction zone. You're going to have friction, right? So in a subduction zone, you have oceanic rock, which, if you remember correctly, is basalt, right? Basalt makes up oceanic lithosphere. And then you're going to have something like andesite, which makes up continental lithosphere. And when the two rub together at high weight, when there's a lot of weight put into that and they're rubbing together, there's going to be a lot of friction, right? They're not smoothly sailing over each other. I'll try to get up close so you can see. I'm pushing them together really hard and I'm trying to slide them across. They don't slide well, right? They're rocks. So that is your sandpaper. This is sandpaper down here, if you can't tell. And then finally, you have this tension. So because it's jolting as it goes, a lot of tension is being built up because sometimes you're going to have pieces of these rocks that aren't going to slide easily, so they catch, right? But that plate is still subduction, so that tension is growing. I'm sorry, I'm really sick too, or I'm getting over being sick. I'm all stuffy. So you have this tension that is growing as this plate is subducting, and that's what these springs represent. So we're going to run this table twice. The first time we're going to run it, we're running it really fast, and you're going to see as we run it really fast, not really fast. I'm not going to. Let me turn it on. You're seeing that the springs are being pulled at different rates, but because it's moving fast, there's not actually a whole lot of jolting that's going on, right? It's relatively smooth. Let me put this back. I might have to fast forward here for a second. Hopefully you stopped fast forwarding if you were fast forwarding this time. Also, these blocks are meant to represent just buildings, right? They're not a perfect model because hopefully structurally they're a little bit more sound. And actually cities like Portland and Seattle now enforce earthquake building measures for their architects. You have to build buildings that are earthquake safe because of this giant earthquake we're predicted to have. Okay, so now what I'm going to do is I'm going to run this slowly. And the reason I'm running it slowly is think about the rate at which these plates are being subducted. If you don't know, I actually don't ever remember millimeter, centimeter wise. But what I do remember is it subducts about the rate a fingernail grows. So think about how fast your fingernails grow. I get acrylics done, and so they're very obviously like growing out. And so I always look at them and I'm like, oh wow, that's how much as the plate has subducted in the last time I got my nails done, which was 2 weeks ago. And so it's not very much, especially considering the scale of the Cascadia subduction zone. It's so vast, you're not actually going to see a lot of subduction happening. It takes millions and millions of years for there to be a lot of movement. So we're going to run this really slowly, and we're going to see what happens. Ooh, I want it even slower than that. So the reason I want to run it slowly is I want you to look at the tension here is really high versus over here. So consider this area as sort of the depth. So this is deeper in the subduction zone and this is shallower. This is what we're going to feel. Wait for this one, when that one moves. So that's what we're concerned about, are these lurches. A smooth transitioning subduction zone isn't as dangerous as these lurches because they'll lurch far and they'll lurch fast. I really hoped it would be a little more dramatic, but the principle is still pretty visible, right? When it runs slower and you get this slower movement, you get higher friction and that tension gets pulled a lot slower. So you have this high tension and you're gonna have those move. And the reason these are separate is because the Cascadia subduction zone doesn't necessarily move as a whole. It moves sort of in sections where it can. And so that's why there's separate bricks here. Okay, so answer the questions in your lab and let your T know if you have any questions.